Right, students here are still playing with a AC generator, and this one is, they've got two magnets and a coil in the middle. It looks very much like a motor, but there's no electricity joined to it. This one we're turning by hand and we're getting the electricity out. So this is a generator, not a motor question. Give us some information about the size of the magnetic field, and this will be helpful as the area. The first question asked us to describe how the magnetic flux through the rotating coil changes. So they're describing the magnetic flux, and it's the coil that is rotating as it makes one complete rotation. You do not need to include any calculations in this answer, and you may use a sketch. It's a bit of a clue. You may use a sketch for your answer. It turns out the sketch is actually the best way to answer this. So if we look at, I'm going to draw my sketch as, what does the flux do? Flux as my coil rotates around. So the rotation is an angle. This is 0 degrees. It's going to go through 90. It's going to go through 180. It's going to rotate through 270, and it's going to get back to where it started from in a complete rotation at 360 degrees. So at the moment, when the coil is perpendicular to this field, so the field lines go from north to south, a lot of field lines intersect and go through that coil, so it has a lot of flux. So when its starting point is 0, it has a lot of flux. When the coil is rotated 90 degrees, so it looks like it's now going to be flat on here, it's now parallel to that field, and none of those field lines actually go through that coil. So the flux now at 90 degrees is 0. When it gets to 180, it's the same position it was to start with, but it's flipped over, so it seems to be facing the other way. So this time the flux is the same as the first one, but negative. At 270, it looks like what I've drawn here, but facing upside down. But again, it doesn't matter if it's negative or positive because it doesn't catch any flux. And then at 360, it's back where it started from, back up here. If we draw these, join these, it's not a triangle like straight lines, but a cosine graph. So I'm trying to make it as smooth as possible. Oops. There we go. So that's the 4 marks on that one. Right. Just before we go on to the next question, you've got the magnetic field here, that's important. We've got the area 30 by 40 centimeters here, and they also say the coil is rotating at 2 rotations per second. This is going to be quite useful for the next question. So let me just open that file up. Alright, generator produces a sinusoidal AC voltage. For a quarter rotation of the coil, that's pretty key. From the point shown in figure 6, it generates an average EMF, so they tell us the EMF 3.6. We have to work out the number of turns, which means the number of loops in this coil. So they've given us EMF, yeah, so this is the equation. EMF, Faraday's law, equals negative N change in flux over change in time. Right, what do we know? Let's work out the change in time first. Remember just before I read that the coil rotates twice per second. It does 2 rotations per second. So that means 1 rotation is in half a second. And this is a quarter of a rotation. So a quarter of a rotation happens in even less time, 0.125 seconds. So that's our time, 0.125 seconds. Right, our change in flux. Remember when the coil was in its original position, we had lots of flux. The change in flux equals flux final minus flux initial. When it's done a quarter of a rotation, so it's flipped over to 90 degrees, there's zero flux. So 0 minus, and now flux, just from memory, equals BA. And in the initial position, the field, if you flip back a page, you'll see the field has 0.03, and the area was 30 centimeters by 40 centimeters. We have to put that into meters. So let's do it before we do the times in. 0.3 meters by 0.4 meters. So we make sure we don't make the conversion up. So that change in flux equals negative 0.0036. Cool. Alright, so we've got everything to put into the equation now. And remember, we're looking for the number of turns. We're looking for this guy n. So we're going to have to do some rearranging. But let's put everything in. So the EMF is 3.6. That equals negative n times. The change in flux is negative 0.0036. And the time is, here it is, 0.125. I'm going to divide both sides. I want to make n the subject, so I want to make n by itself in this equation. The first thing I'm going to get rid of is the 0.0036. So divide both sides by 0.0036. When I do that, I get 1,000 equals, the negatives cancel out as well, n over 0.125. That was from getting rid of the top of the equation, of the fraction. To get rid of the divided by 0.125, I times both sides by 0.125. I might even write it down just so you can see what I'm doing. And times 0.125. So then we get 125 equals n. 125. Last question. This time the students replace the slip rings in this generator with a commutator. It changes the shape of the voltage. Describe the shape of the new output voltage compared to the shape of the original one. You may use a sketch again. They're giving us a bit of a hint here. They use a sketch in our answer. So our original one, and when we use slip rings, and I set it in the equation above, the output voltage is sinusoidal, which means sine shape, sine wave shape. So the original with slip rings, this is voltage versus time. Ooh, losing the plot here. Make that into a T. Time and voltage. Sinusoidal looks like that. And the new with a commutator, commutators in commutator. Slip rings produce AC, commutators produce DC. So it's the same as this, but instead of going positive down to negative, it stays positive. So the same start, but instead of going underneath here, we just have another positive.